PowerPoint, we're going to look at a process called iteration, and then we'll have a brief look at some diagrams called cobweb and staircase diagrams. By the end of the PowerPoint, you should know what iteration is. You should be able to use an iteration formula, and then you should have an idea of what cobweb and staircase diagrams look like, and also understand that the iteration process can converge or diverge. So what is iteration? Well, an iterative formula is a formula that refers to itself. It's a bit like a loop. So for example, if we had the sequence of numbers 3, 7, 11, 15, etc., we could use the formula that says term n plus 1 equals term n add 4. So to get to the next stage, we use the previous result and add 4. So we would continually be using the answer from the previous calculation and then adding 4 to it to get the next answer in the calculation. To find a term, we use a previous term. Here's a dictionary definition of the word iteration, and again it refers to this repetition of a process, and it also mentions in a mathematical scenario the repetition of a mathematical procedure which is applied to the result of a previous application, typically as a means of obtaining successively closer approximations to the solution of a problem. Now this part is very important. This means that using iteration, we are trying to get to the solution of a problem, and gradually, by using the iterative formula, we get closer and closer and closer each time to the real solution. Here's an example of an iterative formula. Xn plus 1 equals the cube root of xn adds 2. So if you knew a term in, let's say, a sequence, and you added 2 to it and then cube rooted, you would work out the next number in the sequence. Let's start by using x1 equals 1. So into the formula we're going to write that xn is actually x1, and we're going to write the value of this as 1. If we put x1 into the right hand side, that means that the left hand side must be x2. So we're working out x2 by substituting in x1. We can see that this gives an answer of 1.4422. To work out the next value, which would be x3, we need to use our answer to x2. So we need to substitute 1.4422 back into that formula. This time we get 1.5098. Next we put in 1.5098 again back into that same formula. This time we get 1.5197. We could keep doing this forever and ever, so putting the previous answer back into the formula to generate the next one. At some point you'll probably notice the numbers of the answers getting closer and closer and closer to something that would be the solution to a problem. If you wanted the answer correct to 4 decimal places, then you could keep repeating this process until you noticed those first 4 decimal places continually being the same. This sort of question could be quite time-consuming if you have to type that formula into your calculator many times. However, you can speed up by programming your calculator to repeatedly perform that iterative formula. So grab your calculator and go through the following steps with me now. If the first number that you're going to input is 1, then just press 1 equals. Your calculator now has that 1 stored on the screen. Next, we want to program it to do the cube root of that answer plus 2. So leaving the 1 on the screen, we're going to get the cube root function. Then we're going to use the ANS answer button and then type add 2. So your screen should now say cube root of answer plus 2. And when you press equals, you'll see 1.4422. That's rounded to 4 decimal places. Now, if you press equals again, it will use that 1.4422 and put that back into the formula. And you'll get the next answer, 1.5098. If we press equals again, we get 1.5197. And you can now just keep pressing equals over and over again, and you'll very quickly get the next set of answers. This is much quicker than typing that formula in many times. You can see here that by the time we get to x, 6, 7, 8 and 9, they're all starting to look very similar. In fact, x, 7, 8 and 9 all show that to 4 decimal places we would have 1.5214. If you wanted to prove that that was correct to 4 decimal places, then you could find the f of 1.52135 and 1.52145, in other words the upper and lower bound, and notice a change of sign. This is something that I went through on the previous PowerPoint looking at locating roots. In an exam question, if it's an iterative question, you will always be given the iterative formula. Have a go at this question. You're given the iterative formula. So if you want to work out xn plus 1, you need to know xn. You need to xn cubed minus 2xn add 5 over 3 and then square root. Using that formula, you need to calculate the values of x1, x2 and x3, giving your answer to 4 decimal places. And we're told that x0 is 1.5. Press pause now and have a go. On the next slide, I'll show you the answers. In order to train your calculator, first of all, you should type in 1.5 equals. 1.5 is now stored on your screen. Next, leaving the 1.5 on the screen, you could press the square root button, then the fraction button, then ans cubed, minus 2 times ans plus 5 over 3. When you press equals, you'll get a third value, but to 4 decimal places it would be 1.3385. Now you can just press that equals button again, and the next value is 1.2545. I think there's a little typo in the booklet. I think that 4 there should be a 5. If we press equals again, the next one is 1.2200. So finally, let's have a look at the different types of diagrams that we need to be aware of, starting off with a staircase diagram. If we draw the graph y equals x, which is the diagonal line, and then a function y equals f of x, let's say then we were going to use that iterative idea to try to get closer and closer and closer to the solution of a problem. Now in this scenario, the solution would be where the graph f of x meets the line y equals x. So we could start off with our first x value, for example 0.3. From 0.3 we could go up to our function graph and then across to the line y equals x. This would give an answer, for example, of 2.15. From there we could go up to our function and then again across to the line y equals x, and this time we get a value of 3.075. If we keep going up to the line y equals x and then back, you can see that that little staircase shape is getting closer and closer and closer to where the graphs meet. So in this scenario, you can see that those x values are getting closer and closer and closer together, they seem to be converging towards the number 4. So this iterative process is getting us closer and closer to the real answer, which is 4. The picture on the right hand side is doing something very similar. If you start with 7.5 on the x-axis, you go to your function and then across to the line y equals x, then go to your function and across to the line y equals x, then go to your function and across to the line y equals x, we have that similar staircase shape, and it's getting closer and closer to where the graphs meet. In these scenarios, the iterative functions have been convergent. They are converging towards the actual solution to a problem. Here are some examples of staircase diagrams which are divergent. In this case, the iterative process fails. If we look at the picture in the top left-hand corner, and we started with an x value of 3.8, from 3.8, if we go to our function and then to the line y equals x, and then back to our function and then to the line y equals x, and then back to our function and over to the line y equals x, we can see that the staircase is getting wider and the values are actually getting further away from the solution to the problem. Remember that the solution are where those two lines meet. If the result is getting further and further away from the actual answer, then our iteration method is failing. This can happen if you start at the wrong point. 3.8 would have been a terrible starting choice here. By starting at 3.8, we are actually going to get further and further away from the actual solution. So your choice of the initial value, x0, is very, very important. If you start in the wrong place, you might actually get further and further away from the real solution. But if you start in a good place, you might get closer and closer, converge towards the real solution. Here are some notes from the booklet that say the other way that an iterative formula would converge is successive iterations alternate between being below the root and above the root. These iterations can still converge to the root, and the resulting graph is sometimes called a cobweb diagram. So in this scenario, we have an iterative formula, and we're told that x0 is minus 2. So if we started at minus 2 on the x-axis and went to the function, then we go across to the line y equals x. From there, we go to our function and then across to the line y equals x. Then we go back to our function and across to the line y equals x. And you can see that we're bouncing up and down above and below that curve. We're sort of going around in a cobweb shape, circling almost around where the actual solution is, the actual solution being where the line y equals x meets our curve. So this is called a cobweb diagram. Final note to take away from this PowerPoint is that the starting value x0 is very, very important. If you start in the right place, you'll converge towards a solution, maybe with a staircase, maybe with a cobweb. But if you start in a bad position, you may diverge away from the real solution. In an exam question, you would be given the iterative formula and the value of x0. You may be asked to say whether the diagram would be a staircase or a cobweb. You may even be asked to sketch the staircase or cobweb diagram.